Hey everyone and welcome back to PrepFusion. So today finally we'll start a new chapter, that is phase control rectifiers. So we have studied about switches and the application of the switches. Now we'll study. One thing is for sure, you can start with this chapter as well. Okay, even if you have didn't study about switches, right? Only if you have studied about SCR, then also you can continue with this lecture, because in the switches part, right, the other switches will not be used in phase control rectifier. Only SCRs will be used. So, and also we don't mainly analyze the switches, we mainly analyze the whole rectifier, and switch is just there as a block. Okay, so but sometimes we have to use the concept of switches as well. So even if you haven't completely studied switches, you can start with this, because this has the highest weightage. This chapter, phase control rectifiers, and the next chapter, that is choppers, these two chapters have the highest weightage. So you must study this, and these two are the most conceptual chapters and the most interesting chapters of power electronics. Inverter is also there, that is also another great chapter. So we'll study. So basically, like you can see from the picture here itself, that what is a rectifier? Rectifier is a converter from AC to DC. And before starting this chapter, right, I will recommend you watch the prerequisite, that is rectifiers, that I have given in the folder above this. I will recommend you to watch that. There as well I have talked about rectifiers and what are those things. Few basic examples I have taken. There I have mainly used diode as the switch, right? Here I will use SCRs as the switch, and obviously diode will also be there, but mainly we will talk about SCRs, and just will take some condition for which the SCR will be used as diode, because SCR and diode are the same, but SCR has just a firing angle where it can turn on, right? It can block forward voltages as well, while diode cannot. Okay, so I will recommend you to watch that prerequisite video, and obviously in the roadmap I have told you obviously how to go along with the flow. That everything I have told. So yeah, you should follow that flow if you are studying from the full course. So now let's start. So here I can see I'm giving my input as a AC and I'm getting my output as a DC. So how do you do that? What do you do? We'll understand. So first of all, in this lecture we'll understand like the introduction to phase control rectifier. What does a phase control rectifiers mean, and what are the different classifications of phase control rectifier? All those things we'll learn. Then we'll start with the analysis of one of the rectifiers. Our first rectifier, that will be half wave rectifiers with pure resistive load. Even though I have taught this in the prerequisite as well, but there I have taught this with diodes, not with SCR. I have done the analysis with diode, not SCR. So I will do the analysis here with SCR. So first of all, what does rectification means? Rectification means AC to DC conversion, that is alternating current to DC current. So behind of me there is a plug, right? There is a switch, so that gives AC supply. But my phone, my laptop, my battery, everything that takes a DC. I've already explained this in the first lecture, first chapter as well. So we need DC, right? We need some device that will convert from AC to DC smoothly, and because DC means smooth, right? Smooth, constant current, and AC is always changing, always moving, and we don't want that. We don't like, our battery also doesn't like that, right? Battery can get damaged. That's why the rectification process involves converting alternating current to unidirectional direct current. Okay, the conversion is achieved using diodes or silicon control rectifiers. So in rectifiers we mainly use diodes or silicon control rectifiers. I will explain why do we use SCR and not any other switch like IGBT, MOSFETs, then BJT, all those switches, why we don't use and why we use specifically SCR. I will explain that. Uncontrolled rectifiers means rectification using only diodes, and control means rectification using SCRs to control the conversion process. Now what does this uncontrolled and control means? Uncontrolled means I don't have the control over the output voltage that I will get. I don't have the control over the value of the output voltage that I will get. That is a fixed amount. Once I make the device, whatever output voltage it will give, right, that will be fixed. I cannot vary it after, like, through a control signal such as firing angle, alpha, right, trigger signal. Previously we used to trigger the SCR at alpha angle. So I am not able to control my output or control my DC. So that's why this is called uncontrollable. That's why we get a fixed DC at the output. Uncontrollable means with the help of firing angle, that is alpha, with the help, like you know, right, we trigger the SCR at an angle alpha when it is in forward blocking mode. We can control this with the help of alpha, and with varying the alpha, right, with the variation of alpha, we can control the amount of DC that we will get out of the output. So we will get a variable DC, which is a function of firing angle alpha. Okay, so that's why controlled and uncontrolled distinction comes, and controlled is better. Obviously you want control over everything, right? How much DC voltage you want. Let's say now you want some like 100 volts of DC, and next day you want 50 volts. There can be a requirement, right? And you want to use the same device. You are using one device, you want 100 volts, and in the other device you connect that rectifier, you want 50 volts. So you want to have the control, okay, after manufacture. So you can do that with controlled rectifiers, but not with uncontrolled rectifiers. So that's why this is a function of alpha. And there is also another converter, that is semi-converter. Basically this both integrates the controlled rectifier and uncontrolled rectifier. Basically here both diode and SCR will be used, and as there is a control nature, SCR is there, so this also will be able to produce a variable DC which will be function of alpha, but this will be a weak function of alpha. Let me check. Yeah, weak function of alpha. Why this will be weak function of alpha? Because here few diodes are also there, right? Diodes are not responsible for controlling the voltage. That's why I have lesser amount of devices here. I have more control devices. Everything is SCR here, so I have more strong control of DC, but here I have weak control of my output DC. But we may use this because this is bit cost effective and we don't want that much of a control. So these are their different use cases. I will explain once we go along. Okay, don't worry about this. This will in semiconductors will come at the end, that is full wave rectifiers. Okay, now like this is the block diagram, and I think this block diagram is shown in the prerequisite as well. Basically phase control rectifiers allow us to control over the phase of the supply voltage. What do you mean by phase? Basically at a certain phase I will use the trigger, and after that I will be able to simply get a constant voltage. Now by controlling the firing angle SCR, that is alpha, we can control load parameters like voltage, current and power. So here, right, I'm getting voltage, current and power, right? Whatever voltage, current and power, I can control that with the help of load parameters. That's why we name this as controlled rectifier. We name this as controlled rectifier, right? So all these things we can do with the help of firing angle alpha. Now what are the applications? So applications of this is speed control of DC machines. If you have studied machines right now, you know we control the speed of DC machine by varying the voltage also. There are different methods as well. Okay, you may know. Operates in various mode. We can control in forward motoring and reverse motoring. If you know, like if you have studied machines, you will understand. If you haven't already, when you will study, you will see there are two modes: forward motoring and reverse motoring for DC machines. Those will understand there. Now forward generating, reverse generating. There are 4 quadrants totally, and we can operate our machines in 4 quadrants, and we can, with the help of this phase control rectifiers, we can operate in different modes. That is, this is basically we're talking about the drives, battery charging and other industrial applications. So like this mobile phone, right, we charge our mobile phone with the help of charger, and if you see on the specs of the charger, right, you will see it is told that it is converting AC to DC. This I have explained in my first chapter as well, and we use this in battery charging and other industrial application. Now why SCR is the most suitable? Like why do we use SCR? We can use some other switches as well. It has good blocking capability. SCRs can block voltages of either polarity, and I want my output to have only one single polarity, that is positive, right? So SCR has the capability to block voltages of either polarity. That's why we use SCR, making them ideal for designing AC to DC controllers. Suitability: due to low supply power, rectifier gate SCRs are preferred for low switching frequency application. So a supply is of 50 Hz. In US it is of 60 Hz. So it is low frequency, right? It is not high frequency. So we don't need that fast switching frequency. And SCRs is not that great for high switching frequency applications. Obviously we can what do you say, we can make them specifically for high switching applications. We have to like change the construction a bit. We have to improve the construction a bit, but for high frequency application generally MOSFETs and IGBTs are used. But as here low frequency is there, and it can block high voltage, because this will be used in supplies, in like power systems. There high voltage, we have to deal with high voltages. So SCR is the best suitable candidate for that. No commutation circuitry. The turning off or commutation of a thyristor by supply voltage is itself called natural or line commutation. So we don't need an external commutation circuit to turn off, because in AC, right, what happens, there is a natural zero, right? It passes through a natural zero, so it will automatically go into the reverse blocking mode from forward blocking mode, and it will automatically turn off. So that is the advantage. We don't need any extra circuitry for turning the SCR off. And I have told you what is commutation, what is line commutation, what is load commutation, what is what do you say, force commutation, right? So natural commutation, force commutation, I have to already explain about that. So yeah, let's get an overview of SCR rectifiers. Basically what things we need to study. So first we will complete the single phase part. Okay, then we'll complete the 3-phase part. And don't worry, you don't need to mug up the formulas. Obviously, there are a lot of formulas, but I will explain them in conceptual manner. I will tell you which formulas you should know, and I will also tell you that how you can remember them, and if you don't remember them, how you can derive them as well. Okay, so that is the most important part. Like with more practice, formulas will get installed in your head, but even if you forget them, right, with conceptually, I will explain the things, everything in a so better manner that you will be able to derive the formula as well. Okay, that part also I will take care of, don't worry, because rectifier there are a lot of formulas, but I will tell you how to remember those formulas and what are the important points that you need to take care of. So in single phase we have half wave and full wave. Half wave means only it will conduct for the half wave of a full sine wave, right? Only up until this region, not until this region. Full wave means it will conduct for the full cycle. It will conduct for the half cycle, this will conduct for the full cycle, and with source inductance that will be later on. We'll like add few non-idealities in the source, then we'll do the analysis with source inductance. Now in half wave, right, we have uncontrolled, fully controlled. Okay, uncontrolled means only diode will be present, fully controlled means only SCR will be present. Then in full wave, uncontrolled, fully controlled, and semi-controlled. In semi-controlled, diode SCR both will be present. In 3-phase also uncontrolled, fully controlled. In full wave also fully controlled, uncontrolled, and semi-controlled. Okay, so in 3-phase the analysis will be basically visualization would be very difficult, but I will try my best to explain everything, right? But single phase you will not get a question wrong, trust me. We'll do so, like the questions also I have framed very well, and like the analysis also I have framed very well with graphs and all those things. You will be able to visualize everything what is happening in the circuit. Now what are the loads? What can be my load? So here, right, here I have a load, and this load is a DC load mainly. So mainly we use this mainly for battery charging. Here, right, RLE means one, resistors, inductive, and E is the voltage. And this is a DC motor load or DC generator load, not generator, DC motor load, you can assume. R means pure resistance, L means inductance, RL means resistance and inductance, plus FD. So FD means freewheeling diode, right? FD means freewheeling diode, and RE means simple RE and RLE, and there will be one RL as well. And like all these loads are there. I haven't written the RL as well. This will be RL, RE, then RLE plus FD. So FD means freewheeling diode. We'll understand what this freewheeling diode means. Also, why is it required in our phase control rectifiers? All those things we'll understand. Okay, so this is the basic overview. We will study in this sequence, right? We'll study in this sequence, don't worry. Okay, and I will teach you uncontrolled and fully controlled in just one analysis. Okay, you will be able to do one simple trick, and you will be able to convert uncontrolled and to fully controlled. Sorry, fully controlled to uncontrolled. Okay, because uncontrolled is the subset of fully controlled, right? So yeah, that I will do. What are the, as of now, before analysis of phase control rectifiers, we need to have few assumptions. Take few assumptions. In study of third-AC systems, SCRs and diodes are assumed to be ideal unless mentioned. So it will be very hectic for us if we assume this as non-ideal and analyze the circuit. First we'll assume this as ideal, and then we'll analyze the circuit. Then obviously we can integrate the non-idealities. Then we study what effect it will cause to our output. Just like transformer, right? First we study the ideal transformer, then we study the practical transformer. Okay, first we'll do the simple things, then we slowly make it more complex. Then during turn on, there is no voltage drop across them. That is the assumption. No reverse current exists under reverse blocking mode. So there is a small saturation leakage current that will exist. That will assume to not exist. Transition time is 0. So there is 0 second transition time. That is basically there is no switching time. On and off time is 0. Holding current is 0, and latching current is also 0. That will assume. But if in the question that it is mentioned specifically, we have to obviously go with the question itself. Trigger circuits are not shown in SCR circuit for convenience. So there is no trigger circuit, just we assume that it has been triggered at some angle alpha. All the SCRs in rectifier circuit are naturally commutated here due to AC supply or load inductance. So for AC supply, we understand whenever this passes through 0, the SCR gets naturally commutated, it turns off. But for load inductance, we'll understand. When we will take example of load inductance, we'll understand that how my inductor can actually turn off the SCR. Okay, how can it turn off the SCR? That also we'll understand. No source inductance is in the circuit is present. No source inductance present in the circuit unless specified. So we will do few problems with source inductance, but at the end, but before that, we'll assume that there is no source inductance in the supply. Okay, now let's understand by part each part, right? So here I have broken down this into 3 parts mainly. Basically this was the supply zone 1, this was the zone 2, that is the rectifier part, and this was the basically the zone 3, this is the filter, and this is the main load part, right? So we'll analyze each part one by one, and that same analysis will follow while understanding each of the different rectifiers. Okay, so the first part is supply, right? Analysis of supply. Supply voltage can be typically of single phase or three phase. So for now we'll only study single phase. After completing the single phase, then we'll go to three phase. Supply voltage is pure AC. That this assumption we have to take. Supply voltage will be pure AC. It will be free from harmonics. What do you mean by harmonics? Harmonics are the unwanted components, right? More of this we learn on our machines lectures. Don't worry. And also I will like give a prerequisite about Fourier series, and there also we will understand what does harmonics mean. It is an independent quantity. So supply voltage is an independent quantity. It doesn't matter, right? When voltage across these 2 points will be independent of everything else on the right hand side or on the left hand side. Okay, supply current is a dependent quantity because supply current can be changed, influenced by the type of the load or converter that is flowing through. Because I am connecting a voltage source, right? So the voltage should be independent. So whatever amount of like plug I put in, or if I measure this through my multimeter, the voltage will always be some 230 volts 50 hertz signal, right, coming from this plug. But the current can change depending on the load register, right? Current can change. That's why exactly this is telling the same thing. In practice, the supply current often contains harmonics and it is not purely AC. So generally we are converting from like AC to DC, right? There will be some complications, and due to that what will happen in the conversion process, the current can have anything, and what will happen is, one most important thing is AC and DC is this. So AC, right? AC doesn't want any constant value in its waveform. Okay, AC hates that. So the most dangerous harmonic in AC signal is DC component. AC signal hates that. We don't want, like AC signal doesn't want that. But DC on the other way around is just the opposite. DC doesn't want any alternating signal in it. It's the worst harmonic for it. So whenever we're converting from AC to DC, right, the supply current becomes like it has some average value, and that is the most dangerous thing for the supply. And how we will mitigate that we'll understand in the next few lectures, right? So that's why it will contain harmonics, and the most dangerous harmonic for AC signal is DC. Magnetic components may get damaged due to heating from harmonics. Let's take an inductor here. If I take an inductor here, and a current I is flowing, right, and it's a constant current. So with inductor, right, what we relate, relate the flux. So flux psi is equals to Li. L is constant and I is also constant. If I is very high, right, I is very high, our flux will be very high. And what do you know? Inductor has specific amount of limitations how much flux it can carry, right? If the flux is too high, the inductor will get saturated and it will get heated. Right? Why am I not finding any colors? Yeah, it will get heated. So huge amount of heat will happen here, and it can damage, right? That's why we don't want our magnetic components may get damaged due to heating from the harmonics. That's why we don't want this. We don't want this, right? We don't want any constant component on our supply current. Those that we will understand. How do we mitigate that? Okay, here are the basically few symbols of supply. So supply can be written like this: Vs and angle, like this. Vs means this Vs, right? Whatever Vs is written, this is always RMS. This Vs is always RMS, and this Vm is always the peak value. Okay, so there are two ways to write this. This Vm is the peak value. Okay, not this peak, and this is the RMS. Okay, just hold on. Yeah, this is the RMS, right? Unless specified, they will specifically say it is a peak. Then only we'll take this as peak. Else, nothing is specified. We'll assume always Vs as RMS. What else? The other thing is this phi, right? Phi means by how much phase angle this is lagging. This is going to be plus minus as well here. Okay, just hold on. Where did you go? Yeah, this can be plus minus here as well. Plus minus. Okay, next this plus minus phi, right? This plus minus phi, I can write this basically it is the phase lag or phase delay or the phase forward of this particular source, right? Generally there is no phase delay or phase like what do you say forward or something like that. It is generally phi 1 is generally 0, right? Now what is this? This is the instantaneous polarity. Now you might say, sir, in AC we don't have any polarity because it is always changing its polarity. This is a notation that at omega t equals to 0, in which side my voltage is increasing. At omega t equals to 0. At omega t equals to 0, if we see this sinusoid, if I write omega t equals to pi by 2 or pi by 4, it is positive, right? And positive, it will give supply like this. This will be plus and this will be minus. Then after one half cycle, this will be plus and this will be minus. So this is just the instantaneous polarity of the source. So this is the notation that we use for explaining the source, for writing the source. Okay, this is the notation that we use. Now let's come to the Fourier analysis. So obviously I have told a bit of Fourier, how we got this formula and what is Fourier series, all those things I have told. Here I will just directly analyze the things in the Fourier series, right? As the source is not purely AC, what will happen is it will have some DC component. It will have some DC component which you understood is the most dangerous component, and it is the harmonic, and it will have other harmonics as well. But like omega naught is the fundamental component, right? And it is the component that we want. That is the frequency of voltage, because voltage is purely sinusoid and we want that only. And why do we want that? That also I will explain here just in a bit. Okay, so this is the fundamental component, and all the other components, right? All the other components, like just hold on, this I is 2 omega t, this will be 2 omega, right? So this messed up, this will be 2 omega. This will be 3 omega. So this will be multiples of the fundamental frequency, our Fourier series analysis. All this will be multiples. Okay, and this will be the fundamental frequency. And then if I want to compute the RMS, right, this I have told in my network theory classes as well, how to compute the RMS for different frequencies. Basically what you do, all of these are orthogonal, right? All of these are orthogonal. Okay, all of these are orthogonal. So what I can do is I can directly square and add them. I can directly square and add them. Why? Because all of them are orthogonal to each other. So like I will remove the DC component. If there is no DC component, then my IS RMS will be something like this. It will be IS1 RMS whole square, IS2 RMS whole square plus right? So here also I explain the same thing. If I have a voltage signal, now even though like we have assumed that our voltage will have only one frequency component, that is this Vm1 sin omega t, but it can have other frequency components as well. We'll just see why these harmonics are not much useful to us. I'll just explain you, right? So I of t will be equals to Im1 sin omega t minus phi 1, Im3 sin 3 omega t minus phi 3. So there is no second harmonic component here, there is third harmonic component, and it is going on. So what will be the power? Power is integration of V of t into I of t over a whole cycle. So if you integrate it, I have proved this in my complex power lectures as well, that if you integrate it, only the signals which have same frequencies, I will get the powers. Which have different frequencies, I will not get the power. And what do we know? In this case, I am getting Vm1 Im1 by 2 cos phi 1, Vm3 Im3 by 2 cos phi 3. If let's say the voltage is pure sinusoid, so there is no other component, right? There is no other component. Then whatever component there are present in the current, right, that will be of waste, because I will only get this component. I will only get this component of power. All the other power I won't get, right? So that is just a waste, right? What is that? That is the reactive power. Okay, that is the reactive power that is getting wasted. Okay, not reactive power, that is the apparent power that is getting wasted. I am not able to utilize it completely. I am not able to utilize it completely. That's why we don't want harmonics. We don't want harmonics because we have to supply that current, right? Because IS1 RMS is sum of all this. IS1 RMS is sum of all this. We have to supply that current, but all these components are not useful to me because I am not able to get my power from that, right? My main power I am only getting through this component, that is Vm1 by 2, only through this omega t component. So here I have written real power is always contributed by I and V of having same frequency. So if they are orthogonal, so this omega t and this 3 omega t are orthogonal, this 2 omega t, 3 omega t are orthogonal, this 3 omega t are orthogonal. Okay, or what do you mean by orthogonal? That also I have explained in my network theory course there. Okay, so they are orthogonal. That's why I cannot simply, like, they will not generate any power for me, and that is a waste for me. That's why I don't want harmonics, because even though I have to supply that current, huge amount of current is flowing and it is getting wasted, I am not able to utilize it. That's why we avoid harmonics. Okay, so what is VRMS? VRMS is this, IRMS is this, right? So basically here IS1 RMS is what? IS1 by root 2. So IS1 RMS, I will just write this over here, because like what is the RMS of a sinusoid? It is peak by root 2, right? So this will be, I will just write here in short, IS1 RMS will be IS1 by root 2. Okay, so all this I hope you have understood how to compute VS RMS, how to compute I RMS. Okay, now here one interesting term comes, that is a fundamental power factor. So what is the fundamental power factor? Now as computing the power factor is what computing the, like what is the power factor? Power factor is the angle between voltage and current. Okay, but as I am not getting my overall power from all of the current, right? All of the current, from what I am getting the power? I am getting the power from this, and this is known as the power from the fundamental component. And this cos phi 1 is actually known as the fundamental power factor. This is the angle between the fundamental components of voltage and current. Okay, so that, and this is the useful thing, that's why this term, we have made this term separately, because this is very useful to us, because only this is generating the power, other components are not. But in this case you can see cos phi 3 is generating the power, but most cases our voltage will be pure sinusoid, and only then this will generate only this component and not this component. Okay, so the fundamental power factor is the cosine of the angle between the fundamental components of voltage and current. As explained, it represents the maximum possible power factor of a system without using power factor correction techniques. So if you don't use, like we have to use power factor correction techniques as well, because the power factor is reducing. And what is the power factor? The amount of active power that I can generate with the fraction of active power from the, the fraction of apparent power that I can get, and that is equal to the active power, right? So we have to use power factor correction techniques to improve the power factor of the system. If we don't use them, it is the maximum possible power factor that I can get. Why? Because after this the power factor will only degrade, because the current angle will only increase, and that will degrade my power factor. Fundamental power factor is also known as displacement power factor. Why? Because how much it is displaced from the fundamental component. So these are the names that you need to remember. And here, like I have written Vs, right? Vs is the supply voltage. It has no harmonics, and this is the IS1. This is just a component of the fundamental component of the current, right? There are many other components as well, and IS1 can be written like this, voltage can be written like this. In short, it is known as FPF, fundamental power factor, or DPF, that is displacement power factor, equals to cos phi 1. Okay, I hope you understood. This is simply the power factor of this, right? This is the fundamental power factor, right? The angle between, cos of angle between the fundamental voltage and current. Okay, now what is operating power factor? Operating power factor is basically the ratio of the real power to the apparent power, and you can say the cos of the angle between the overall voltage and current. So I will just copy this, cosine of the angle between overall voltage and current, not the fundamental components, overall voltage and current. So just hold on, just paste this over here. The operating power factor is the cosine of the angle between the overall components or the resultant, taking into account all the components of voltage and current, right? Cos of the angle between voltage and current. This is the overall voltage and this is the overall current, right? If I add all this, what is IS1 RMS? It will be the same formula that I used previously, and this is my VS RMS. This is only one single, and IS1 RMS is simple. It is summation of all this. So cos phi, overall operating power factor or supply power factor, because load power factor will be depending on the load, but supply power factor will be depending on the angle between voltage and current. And this is very important to us, because we want to understand how much of the fraction of the apparent power I am getting as my active power. Okay, the ratio of the real power to apparent power. Computation of fundamental power factor requires analyzing the Fourier components of the supply current. Okay, this will be for the fundamental components, not fundamental power factor. Computation of operating power factor, like for operating and fundamental power factor. Operating and fundamental, both of these require the Fourier series analysis of the supply current, because with the help of Fourier series analysis I can break it down into this type of components, right? Into this type of components, else I won't be able to break it down. Okay, so let's go to a new term, that is distortion factor. So I have already told you that this level of things, right, these IS2 RMS and all these are undesired for us. Why? Because they don't contribute to any active power. So these are undesired. Okay, these are undesired. Okay, as these are undesired, there must be a factor that can be able to compute all this, right? What amount of power is undesired. So now if I compute the overall power, like there is a one factor known as distortion factor that I will derive with the help of overall power. So what is power? I've already explained, right? What is power? Power is power over a cycle of a periodic function. It is 1 by 2 pi from 0 to 2 pi of Vs into Is. I'm computing the supply power this time, d omega t. Okay, now we know, right, what is power? Power, mainly our power is Vs RMS. We have already computed it. Vs RMS into Is RMS into cos phi 1 into the fundamental power factor. This will be the power, and all the other components will be 0. Now what is cos phi? What is cos phi? So we can write this in a different manner as well. What we can write? We can write this like this. Okay, we can write this like this. sorry, this will be IS1, right? Sorry, this will be IS1 RMS. This is my active power that I have just computed here, right? You can compute for yourself. Where did it go? Where did it go? Here, right? This will be just the power, basically VS1 IS1 RMS into cos phi 1. This will be the component, because I don't have a 3 omega frequency over here. So what I will get is that basically VS1 RS cos phi 1. Now how else can I write it? I can write it like this as well, right? PS can be written like this as well, and cos phi will be much smaller here. It will be VS RMS into IS RMS into, just hold on, cos phi, right? Into cos phi. This can also be written. This is also a formula for power, because that is the definition of this, right? PS is equals to what? SS is BS RMS IS RMS into cos phi. This is the formula for PS. So these two I can equate, and if I equate these two, the ratio of IS1 RMS, I will just write it over here. Just hold on. Yeah, I can go to the next page. If I just write the ratio, this will be a distortion factor. What can I write as my cos phi? What can I write as my cos phi? Cos phi is equals to IS1 RMS, or IS1 upon IS also we can write IS1 RMS upon IS into cos phi 1. Now here, right, what is this? Like, this is our, what is this component? Just hold on. What is this component? This is our power factor. This is our power factor, right? Power factor is cos phi. And what is this? This is the fundamental power factor. This is the fundamental power factor. Now this term needs a name. This is what? Basically, this is the total supply current, IS RMS I need to write. Resultant supply current, and this is the supply current for the fundamental component. So here, right, I can name this as distortion factor, because this is the amount of distortion that I am getting, because IS1 is the required one and IS is the overall component. So this is just a name for this. This is known as the distortion factor. In short, we write this as DF into power factor. So we can write our power factor like this. And what we can observe is, obviously distortion factor will be somewhat less than 1. Okay, distortion factor will always be less than 1. DF will be less than or equals to 1. It cannot be ever more than 1, because IS1 RMS always has to be less than IS RMS. So hence, I can say that power factor will always be less than fundamental power factor. Hence proven, right? I just told you that our power factor will always be lower than this is the maximum possible. Fundamental power factor represents the maximum possible power factor. Okay, if the displacement factor is 1, that is the maximum possible case, only then power factor will be fundamental power factor. It will be the maximum possible power factor of the system, else it won't be, right? I have explained you. So I have explained all these things. So in machines, sometimes this is called as the like in machines you will study this sometimes fundamental power factor is called as the K theta, and this is called as the KD, the displacement factor. All this we'll study in machines as well. Look, so this is the formula. These few terms you need to know. These are the things you need to remember. So yeah, this is important, and that's why we do the harmonics analysis so in depth. So here I have a question with you. The input voltage and current of AC/DC rectifier is given by this. Vs is this. Now this is the perfect example of a rectifier. So here in a rectifier, right, the supply voltage will only have one component, the fundamental component. The supply current will have multiple components, right? So can you compute the input power factor now? How will you compute the input power factor? So basically, right, just hold on. Yeah. So basically, you know the voltage, you know the current. You can compute the power, and from there, if you take the ratio, like you can compute, like what is power factor? you don't need to remember anything. I will solve with basics. Okay, I won't use the terms fundamental power factor or distortion factor. Obviously, you need to remember those, because if they specifically ask you fundamental power factor, you can directly say from this, right? What is the fundamental power factor? It is the angle between cos of angle between the current and voltage. What do you see? Current angle is minus pi by 3, and this is 0 angle. So what is the cos? What is the angle? Pi by 3. And what is the cos of it? Cos pi by 3. Cos 60. What is cos 60? Cos 60 is half. So fundamental power factor is 0.5. Now, as my current is lagging, right, it will be 0.5 lag. As there is a negative angle, current is lagging. So I hope you know what is lag lead. Current is lagging, that's why this will be lag. If here, let's say current would be leading. If the current was leading, then it would have been capacitive. It would be lead, power factor lead. Generally, in rectifiers, this will be lacking most cases. This will be lacking. Current will be lacking always. So we have computed the fundamental power factor. What is the distortion factor? Distortion factor is the IS1 RMS upon IS RMS. What is IS1 RMS? It is 10 by root 3. What is IS RMS? It is 10 by root 2. Sorry, it is not 10 by root 3. Sorry, IS1 RMS is 10 by root 2. So IS1 RMS is 10 by root 2. What is IS RMS? IS RMS is 10 by root 2 whole square plus 4 by root 2 whole square plus this, right? 3 by root 2 whole square. We'll just compute that. So cos phi is basically what? PS upon SS, right? Basically the apparent power, active power upon apparent power. So what is the active power? Active power is very simple, right? Active power is very simple. It is basically the VS RMS into IS1 RMS into cos of phi 1. That is my active power. So this is simpler. So PS will be VS RMS into IS1 RMS into cos phi 1. And basically what is this? VS RMS is what? 230, right? What is IS1 RMS? It is 10 by root 2, right? Peak upon root 2 into cos phi 1. Cos phi 1 is cos of pi by 3, which is half. So this will be 2300 divided by 2 root 2. I'll just quickly compute it. Just hold on. I'll just quickly compute it. Quickly compute this value. So this will be 813.173 watts, right? 173 watts. Now I need to compute the SS. What is my SS? Apparent power. It is basically VS RMS into IS RMS. All this I have explained in my complex power chapter. So you have to go through that if you are not able to grasp this thing, right? So I won't go over this. Whatever is new, that I will explain, but whatever I've already taught, I won't explain. Okay. So VS RMS into IS RMS. So VS RMS is what? Basically VS RMS is 230 again. And IS RMS is what? IS RMS I need to compute. So if I want to compute IS RMS, right? I can compute it like this. So my IS RMS will be somewhat like this. It is IS1 RMS plus IS2 RMS whole square. So 10 by root 2 whole square plus what is it? What is IS2? It is not IS2, it is IS3, right? Because it is a third multiple. 4 by root 2 whole square plus IS5 RMS. It is 3 by root 2 whole square. 3 by root 2 whole square, and at the all the components are finished, so I have to take the under root of this. I have to take the under root of this. So what will be this? This will be 100 by 2, that is 50, plus 16 by 2, that is 80, plus 9 by 2, that is 4.5. Okay, 4.5. So this will be what? I'll just compute this real quick. 50 plus 8 plus 4.5 under root. This will be around 7.9 amperes. Okay. So what will be my SS? It will be simply 230 into 7.9, right? So it will be, I will multiply this with 230. I will get something around 1818, right? 0.3. Okay, 1818.3. Now what I can do is I can directly compute the power factor. What will be cost wise? This is a supply power factor, right? They have specifically told us the input power factor. Here input means this supply power factor, right? That is the power factor of the supply. So because supply voltages and currents are given, so here my active power is 813.173 divided by the apparent power, that is 1818.3. so this will be okay, I have made some mistake. Oh no, I haven't. 813.173, this will be around 0.44. so 0.44 or 0.45, and as the angle is lagging, current is lagging, like overall I can see all the components of the current are lagging itself, so it will always be lag from the voltage. It will always lag from the voltage, so this will be lagging. Okay, this will be lag. I hope you understood the power factor calculation. So there is another term known as total harmonic distortion. So total harmonic distortion means how much amount of harmonics are present in the supply current. So this I've also explained in my prerequisite as well. I will not go through, like totally here. I have explained in my prerequisite as well. TSD is a measure of distortion of a signal caused by harmonics. It quantifies the deviation from the ideal sinusoid. Okay, how much am I deviating from the ideal sinusoid? TSD is calculated as the ratio of sum of the powers of all harmonic components to the power of the fundamental frequency. Okay, so like this is the ratio of the all harmonic components to the power of the fundamental frequency. So here it is Vs into power due to all the harmonic components divided by Vs into the fundamental component. So here only Vs gets cancelled, only IH RMS, that is all the other components except the fundamental components will be present over here. The RMS value of that and just the RMS value of the fundamental component will be present in the denominator, and the ratio of these two will just be my THD. THD is crucial in assessing the power quality, the quality of the waveform. With lower THD values indicating less distortion, that the amount of THD is lower, that means the harmonic component is lower, the fundamental component is higher, that means the distortion in the waveform is lower. So this is a good factor for assessing the criteria of the waveform, assessing the quality of the waveform. Okay, so all these are there. Basically you can see the formula. This is a basic intuitive thing. Now what can they ask from the supply? So there is rectifier, right? There is a rectifier, and right now I am like analyzing the zone 1. In the zone 1, what are the expected quotients? So they can ask the supply voltage, that will never change. Vs will never change, right? Vs will always be sinusoid. I will say this, no change. Supply voltage will never change, but supply current, this can change, right? Because it depends on the load. Now power factor, they can ask supply power factor. I will already compute it for one of the examples. Then fundamental power factor or fundamental displacement factor or fundamental power factor, these are the same thing only. Or they can ask distortion factor as well. So here you have a wrote in it. This is known as fundamental displacement factor. Have I okay, yeah, fundamental power factor is also known as displacement power factor. This also you should know, right? So this would not be FPF, this will be DPF, right? Displacement power factor. Sorry about that. Yeah, they can ask the total harmonic distortion. They can ask the average RMS maximum values of VSIS, voltage and current. You can find out, right? We have already just computed it. They can ask the active power consumed from the by the supply, reactive power, and the given from the supply, active power given from the supply, reactive power given from the supply, and the apparent power. Phasor diagram, that is the least possibility. They can ask phasor diagram, but all these things they can ask, right? And I hope you know all this, how to compute this in complex analysis, complex power chapter. I have already taught all this. Okay, so now let's solve a gate 2011 question. This came in electrical, gate 2011. So I will give you this as homework, because this is just the same question that we just solved, right? That we just solved over here. This is just the same question, but this came on gate. So you apply it and you try to solve it, and I will put this as a homework, and I will like write the solution in the next lecture. Okay, so this is just the same concept. You use the same concept here and you will be able to find out the answer. So now let's come to the analysis of converter portion. Just hold on a second, let me check if everything is fine and recording. Yeah, analysis of converter portion, right? So in converter, what can they ask? They can ask the voltage and current waveforms of the converter's internal devices, that is the SCRs. Then they can ask the average RMS of voltage and converter devices. Then on time and like for how much period of time they are conducting. Okay, this is also known as the conduction angle, also known as the conduction angle. Then forward blocking period, because we know SCR can block forward voltage as well as reverse voltage. For how much amount of period it is blocking the forward voltage, for how much amount of period it is in reverse blocking, okay, and the firing angle and the triggering angle. What should be the firing or triggering angle? All these things they can ask. So we'll solve this in the questions. There we'll understand this. Okay. So what is firing angle and triggering angle? Even though I've explained this previously as well, I will explain this here again. It is the angular delay, firing angle or trigger angle is the time delay. Angular okay, just hold on. It is the triggering. Just hold on. This is wrong. Angular delay or firing angle or triggering angle is the angular delay or the time delay in applying the gate pulse to an SCR after it becomes forward bias or after it is in forward blocking region. After it is in forward blocking mode. Okay, when it is a forward blocking mode, we can always turn on the SCR just by triggering in the gate circuit. Now, when do you want to trigger? That depends on the firing angle. Okay, this is the time delay or angular delay. So, let's say my sinusoid is like this. My voltage across the thyristor is like this, right? Let's say omega t is this, and this is my V of t. Okay, and voltage, that this is the anode to cathode voltage. The voltage across it is like this. Now, when can I turn on the thyristor? In this region, right? I can never turn on the thyristor. In this region, I can never turn on the thyristor because this is in the reverse blocking mode. And this is in the forward blocking mode. And in this region, I have control. I can turn on the thyristor. And let's say I use a trigger signal at omega t equals to alpha. So if I use a triggering signal at omega t equals to alpha, like up until here, the thyristor was off, right? Because it was in forward blocking region. Now, as soon as I triggered, what will happen? It will turn on. The thyristor will turn on, and the voltage across it will become 0. Okay. So basically, it is the angle at which the device starts conducting. This is silly, right? This is just hold on. Need to reduce the size, else this will be always coming in the picture. Starts so this is the thing, you can read the definitions over here, but like this is the main criteria of firing angle. So this is already, you know, all this like in visualization here as well, I have explained that, like let's say this only, right? So here, what will the voltage across VT? So this is the VT, right? This is the VT. VS is sinusoid. This is a VT. So here, right? Here, what do you see? Current through is 0. So this is like grounded, and this is the VS. So overall VS is coming across this thyristor, and this will be sinusoid. And only in this region, I will be able to control my thyristor turn on. Okay, forward blocking region, and in this region I won't be able to control, right? So my alpha in this case, right? My alpha, that is the firing angle, can have a range from pi to 0, right? It cannot be more than pi because I cannot even control my device. And this concept of firing angle will be used only for fully or semi-controlled devices, because in uncontrolled it is diode, and diode doesn't have any firing angle or firing circuit, right? Because diode turns on, it doesn't have any condition, it cannot block forward voltage, right? Now in this pi, I have already explained, in this, after this pi, what will happen is, why my range is from 0 to pi? Because after this, right, there is natural commutation is happening. Okay, after this angle pi, natural commutation is happening. So obviously thyristor will get turned off after this. I don't have any control over this. Now next is natural commutation period. What is natural commutation period? The period during which my SCR is transistors to reverse blocking mode from forward conduction mode. So if the SCR was more on here, just after this, right, in this case it is in reverse blocking mode. The period for which the SCR remains in reverse blocking mode is known as the natural commutation. Okay, so basically here two terms are there. So here, right, I can write this as natural commutation period. So just hold on, this will be like my what is like for in this case, right, in this case, what in this angle alpha my device gets turned on, in this angle alpha my device gets turned on. So what is the forward blocking period? So it blocks from 0 to alpha only. After this it cannot block forward voltage because my device has been turned on, triggered. So it is only alpha, right, it is alpha. Or I can say, what is the time of forward blocking? It is omega t into t, like sorry, omega t equals to alpha, right? So TFBM will be simply alpha by omega. Now what is the natural commutation period? We write our natural commutation period like something like this. Or first of all, I can define the conduction period as well. What is the conduction period of that SCR in this particular case? If I trigger it at alpha, the conduction period will be T on, or I can write omega into T on, will be from what? Will be from alpha to pi. Okay, after that it will be natural commutated because it will be in reverse blocking mode. Okay, so here it will be pi minus alpha to omega. Okay, it will be pi minus alpha to omega. So now what is the natural commutation period? What is the natural commutation period? So here, right, natural commutation period will be when the SCR is in reverse blocking case. In this case it will be equals to omega t into Tc. We write it as Tc equals to only pi, right? For this overall negative half cycle it is totally naturally commutated in reverse blocking mode. So omega into Tc is equals to pi. So T is equals to pi by omega, right? So this will be my natural commutation period. So all these things are there. So I have defined you everything for the period thing. There is a huge confusion. I have tried to create all the confusion, all the three regions. Only these can be asked. This is also known as the conduction angle gamma. This is also known as the conduction angle. Conduction angle. For what period it is actually conducting. Okay, fine. So there can be losses in the converter. From that also they can ask questions. So for ideal converter, right, power loss will be 0, but our converter isn't ideal. I've already explained the switching losses. It can be computed as a linear piecewise model. So what will be the loss? The loss will be this, right? I've already derived all this in the first chapter. Okay. One thing to notice here is that I've already explained in my first chapter as well. If you see this IRMS, right, this R can dissipate, R can dissipate all components. This R can dissipate all components. It can take in all components. So that's why IRMS is here, right? So that's why there is a matching from AC to AC. Like I am talking about specifically the power. And if you observe, what is this V? V is this DC, right? With V, that's why a DC comes. This thing I have intuitively explained in my chapter 1 as well. So this is matching with DC to DC, right? Because V is DC and I average also needs to be DC. That's why only the components which are orthogonal, they won't dissipate any power with each other. But the components which have same frequency or which are not orthogonal with each other, they will dissipate, okay, the power. So this is IRMS square R on into V on plus I average. This is the total loss. Now, what is the total loss in the converter? It is switching plus conduction loss. When it is turned on, this will be the loss, and switching loss will also be there. This will be equals to PS minus PO. What is PS? PS is the power given from the supply, and this is the power taken from the load. Now generally our converter is 100% efficient, so that is our assumption. So PS will be equals to PO if there is no loss, and efficiency of there is no, like, it is ideal converter, right? It is ideal converter is okay. So like, now let's go to the third section, that is analysis of load. So we won't mainly focus on filters. I will explain a bit about filters also. I'll do the analysis, but from filters questions will not come. Questions will come from supply side, from converter side, and from load side. These three sections. So on the load side, right, here load must be DC, because we want DC, right? We want DC. So obviously I'm converting from AC to DC, so I will want DC. That's why obviously load must be DC. Elements may be RE, RL, RE, RLE. Okay, these elements are there. What is R? R is resistance. E is this battery. RL is RL. RE is this RLE. So these, we analyze all these loads with different converters. Load must operate in continuous mode. So what do I mean by continuous mode? Because I'm in DC, right, and DC doesn't like zero current, right? DC doesn't like zero current. We want to operate in continuous mode. Here continuity doesn't mean that continuous graph. It means that my current will not be equals to zero. Yeah, I was actually removing that point. Now what I was saying here is that in steady state, short circuit of load is allowed, but open circuit is not allowed. Why? Open circuit means what? Current is zero. Current is zero, and I don't want that, right? I don't want that on open circuit. I don't want my current to be zero, because I want a continuous load flow. That's why short circuit is allowed, because we'll see with the help of inductors we can make it short circuit and current will flow continuously. But open circuit is not allowed, because current will become zero, and that we don't want. We don't want our current to be zero in the circuit while we are charging. We don't want that. Okay, so that's why we generally don't use use capacitors. Okay, because at steady state capacitors are open circuit, right? Capacitors are open circuit. So now let's go to the another question that like expected question that can come from load side is that obviously voltage of like the waveforms of voltage and current, average RMS, maximum values of voltage and current. This is the most important part. Mainly this is what we analyze, but like those portions can also come, but this is the most important part. Power, reactive power, apparent power. Now few key points you need to understand is, in general, the output voltage and output current will not be pure DC. Just with this rectifier we need extra component, that is filters. VO and IO will be pulsating DC. This I have explained in my prerequisite as well. Why will this be pulsating DC? Here continuity of current means the current always flows in the given circuit. It is not equal to zero. This also is known as continuity of current. Is also can be said that continuous conduction. Continuous conduction. Okay, so this is not the same definition as continuity of graph. Next, the output of the converter contains two components, that is DC component and AC component. So DC component is obviously desired because our load is DC. That's why DC component is obviously desired, and this is the undesired component. Okay, this is the undesired component. You will learn more about this in the machines. Now here I have explained specifically what does continuity mean. So if there is discontinuous conduction, that means current will be zero for a considerable amount of time. If there is continuous edge of just at edge of continuous, so what will happen is current will be zero for an instant. Here at omega t equals to 2 pi, it is just zero for an instant. Again at omega equals to 4 pi, it is just zero for an instant. That's why this is known as edge of continuous conduction. Next, continuous conduction means current never becomes zero in a cycle. Okay, it is always some value. Then continuous ripple free conduction means output current is constant. Ripple free means there are no ripples. This is rippling, right? From certain range there will be no ripples. That's why this will be always constant DC. That is what this continuity of current or continuous conduction means. So again, what will be load power now? So load power will be simply, if I have a RLE load. Now what you know is that inductor doesn't take any power. So power through inductor, that I will derive as well. Power through inductor P of L I will derive later on, don't worry. In a cycle, right? In a cycle, P of L, I will write this. In a cycle, power consumed by in a cycle will be zero. Power consumed by that inner cycle will be 0, right? Okay, so why? Because whatever energy it will take in, right, it will it will provide back the same energy. I will prove this in while we're studying the inductance. I prove this, don't worry. Okay, so hence the power will be consumed only due to this R and E. No power will be consumed in this inductor. So what amount of power it can consume? Again, all components, right? DC to DC matching, AC to AC matching, that is IO RMS whole square into R, and this battery can only consume but DC power. That's why this is E into IQ average. Okay, I got it. Now load DC power or load operating power. Now what is load DC power? So if they specifically asked us to compute the load DC power, right, I have told you, right, there needs to be matching. So if they have asked us to find DC power, okay, matching, I will also derive this. How did this come? Hence this also needs to match, right? Both of these needs to be DC. Then only I will be able to compute DC power. Now why am I interested in DC power? Why? Because I'm converting from AC to DC, and I want to know how much, after conversion, how much of the portion of the power that I'm receiving is DC and not AC, right? Because mainly I'm converting from AC to DC, so I would like to know how much of that overall power that I am getting at the output of the rectifier is DC. So there is a term known as efficiency of the converter. So if nothing is mentioned, you will define your efficiency of the converter like this. It will be the contribution of DC component to the total power available at the output of the converter. So converter is giving me some power, but how much of that power is the DC component? That I want to know, and that will be called as the efficiency of the converter, unless specified definition from them. Unless they specify the definition by them, you will assume the definition of efficiency of a converter like this. It is PDC upon PO. So converter is giving me some output power here, right? It won't be totally DC. Some of it will be AC, as seen from this IO RMS into R square, because this is not DC, right? Here there is a AC component. There is a AC component present in this current, right? That's why it will dissipate some power. So that's why we need to find out the ratio, and this will be give us the DC power. Okay, this will give us the DC power. I will also prove this, how I get this VO average or average, while we'll do the analysis of a rectifier. Okay, so here, right, what do we mean by DC? So if we do the Fourier analysis of the output voltage, we'll see we'll have an average that we want, that is the DC component, and the other components, other frequency components, that is the ripples. They are known as the ripples, as explained. Okay, so there will be higher frequency components. Those are ripples. Those are undesired, and this is the desired. So for load, right, these are undesired, and this is the desired. For supply, I have told you this is undesired, right? DC component is not desired. Only one fundamental component is desired. So different things are there for different sides. You have to understand. You have to make both sides happy. Just like in a couple, right? You have to make your girlfriend happy as well. You have to make your best friend happy as well, right? So you have to manage both ends, right? So your girlfriend may not like your best friend may not like your girlfriend, but you have to be neutral. So that's why you have, your load doesn't like AC components, your supply doesn't like DC components, but you have to manage. How do you manage and how to rectify all this? There are few power factor correction techniques and all those things. Okay, so and for ripples, for load side, we install filters which reduce ripples. This I have explained in my prerequisites. For the supply side, we install power factor correction devices which improves the power factor and which reduces this DC component. Okay, so ripples are written like this in terms of voltage, and the RMS will be this. The formula is already explained. So basically, how I can write the RMS? VO RMS will be simply, all of these are orthogonal, right? All of these are orthogonal with each other. So VO RMS will be VO DC whole square plus VO AC whole square, because this whole thing is AC component, and this thing is only DC. This thing is only DC, right? So ripples of VO will be VO AC. In the load side, right? The AC component will be the ripples. So that is equals to what? That is equal to simply this, right? If I write this, if I compute VOAC, it will be VO RMS whole square minus VO DC whole square whole under root, right? So what will be the ripple factor? Ripple factor will be simply the VOAC factor divided by VODC factor. This I have explained in my prerequisite as well. This will be simply this. Okay, this is just a formula. This is just an intuition. So mainly what you should remember this one. Okay, what is ripple factor? Okay, ripple factor means how much ripple is present at the output. Okay, ripple means how much ripple. So ripple component is VOAC, and what do we want? I want VODC. So the ratio of VOAC and VODC will be my ripple factor. That is one point. Then how do you compute VOAC? I know VORMS square equals to VODC whole square plus VOAC whole square. From there I can compute the VOAC at that, and if I just put this in the formula, I will get it. Okay, that's how you remember. You don't need to remember all this, right? Just remember few things and make a mapping of all those things. Make a mapping. You write these things is in short notes, and that's it, right? And whenever you write this in short notes, you in your mind, whenever you go through the short notes, try to remember all the other things. Okay, VOAC upon VODC. How do I compute VOAC? What is VORMS? All those things should go in your mind. Then only you don't write everything in short notes. You just write this in short notes, and from this, after observing this, can you recall? Okay, what was this? What was that? That is how you revise. Right? That is how you revise. Okay. So this is the first rectifier that we want to analyze today. So only we will be able to analyze only up until this. Okay. So what is this? This is the single phase half wave rectifier with pure resistive load. If I have a pure resistive load, how will the waveforms look like? How will the analysis look like? So first of all, here we assume that our SCR is ideal. SCR is ideal, hence there is no switching loss. So this is also called one pulse converter. Why, I will explain in a bit. And this resistor is pure. This resistor is pure resistance. And if the symbol is like this is SCR. This is a control. We can control it with angle alpha. And if this is symbol is like a diode, this is uncontrolled. This I have uncontrolled one. I have already done the analysis in my pedagogy chapter, but there is one simple condition that will convert this from controlled to uncontrolled. You just make alpha equals to 0. Sometimes we have to make alpha equals to alpha minimum, and that will make it uncontrolled, right? Uncontrolled. Alpha minimum is what? The minimum angle at which I can trigger the SCR. Okay. So let's do the analysis. So we will go step by step. First of all, I will understand when is this SCR going into forward blocking mode. When is SCR going to forward blocking mode? So I will initially assume that SCR was off. If SCR is off, what is the voltage across my thyristor? What is the voltage across my thyristor? Basically, this current is 0, right? This current is 0 because SCR is off, no current is flowing. So VO is 0. So if I apply a KVL, my minus VS plus VT will be equals to 0. So Vs will be equals to Vt, or I can write Vt will be equals to Vs. Vt will be equals to Vs. So Vt is equals to Vs. What is my Vs? Vs is simply sinusoid. Right? Vs is simply sinusoid, and I have already explained this previously as well. We'll do this again. Okay, this one I'll just draw a rough sinusoid. Okay, and what I observe is that this is Vm. This is minus Vm. Just this is a rough drawing. Okay. Now in this region, right? What is this? This is the reverse blocking mode because the SCR voltage is negative. So I can never control in this region. Okay. Reverse blocking mode. I can never control in this region. Can't control. Now what is this region? In this region, right? My SCR is in forward blocking mode. I can control in this region. I can control in this region. Okay. Because if I trigger my SCR now, my SCR can turn on. Even though it is blocking the voltage, once I trigger with the gate voltage, it will turn on. So this is the period of forward blocking. What is the period of forward blocking? Period of forward blocking is from 0 to 2 pi. Not 2 pi, sorry. From 0 to pi. This is the pi, right? Pi, this is pi, this is 2 pi. Now, what can my alpha like? My alpha can be from alpha equals to 0 to alpha equals to pi. After alpha equals to pi, can I ever trigger my SCR? No. After alpha equals to pi, I can never trigger my SCR. My SCR will never turn on after alpha equals to pi. Okay. So this is my range of alpha. So whenever you are analyzing a rectifier, right, you have to find out your range of alpha, right? Like not from question point of view. Whenever you are analyzing, from understanding point of view. From question point of view, how to solve questions, that I will explain. But now we are just analyzing the SCR. So for analysis point of view, you just first understand in what range I can control the SCR. In this range, right, from 0 to pi. After this, I won't be able to control my SCR. Okay. So now what next? I have understood that I can control my SCR from 0 to pi. Now I will do the analysis. What is analysis? I will divide it by case. So first, from 0 to alpha, what is happening? 0 to alpha, my SCR is off. Omega t equals to 0 to alpha, my SCR is off. The current is 0 amperes. So my IS is what? IS is the source current. It is same as the thyristor current. Both are in series. It is same as the load current. All of it is 0 amperes. All of it is 0 amperes. So if my IO is 0, right? My VO is simply IO into R. So it will be also 0 volts. But my VT, right? VT will be simply Vs. Okay, Vt will be simply Vs, and what I see, my Vt is greater than 0, because in 0 to alpha, as alpha is lower than pi, Vt has to be, Vs has to be positive. As Vs is positive, it will be Vt will be positive, and hence I can totally conclude that it is in the forward blocking mode now. Forward blocking mode. Now, once I trigger the SCR at omega t equals to alpha, once I trigger the SCR, the SCR turns on. As soon as the SCR turns on, what will happen? This will become short circuit, right? A switch will close and this will become short circuit. I have assumed this is an ideal switch, hence there is no turn on time, there is no losses, there is no resistance, there is no on voltage, on drop, there is no on resistance. So add omega t equals to alpha, SCR is triggered. SCR is triggered. Now as soon as it is triggered, SCR will turn on. Okay. Next, current will start to flow. Current will start to flow. Hence, what I can say is that this is short circuit. Now my Vt becomes 0. My VO becomes simply Vs, right? If I apply KVL, VO becomes simply Vs. Now what is my Is or IT or IO? All are in series. It will be simply what? Simply VO by R. It will be simply VO by R. It will be Vs by R. Now one thing you have to keep in mind, current can never flow in this direction, right? Because this SCR will never allow current in this direction. Current can only flow in this direction, right hand side. And is this true, right? This is true because this Vs is greater than 0. Hence, my Is is greater than 0. Okay, Vs is greater than 0. Hence, my Is is greater than 0. So, like, how can I define my IO? How can I define my IO? So, Is is this value, right? Is is what? I can write Is is equals to Vs is what? Vm sine omega t by R. Okay. Now, can you define the peak value? Can you define the peak value of IO? So I will just copy this. What will be the peak value of IO? Okay, this didn't copy. The peak value, that is IO max, can be defined in two ways. So when can this get peak? So peak happens at pi by 2 when sin omega t is 1. After that it becomes lower, right? So I can have two peaks depending on the trigger angle. That's why now you can see that alpha is the control level. Why? Because IO max can be two things. It can be Vm by R when my alpha is less than or equals to pi by 2. So yeah, because I'm triggering the SCR less than pi by 2. So what is happening is my device is always on after this region, right? And I am getting a peak voltage at pi by 2 and that voltage is coming across my output. Now if I trigger my SCR somewhere around here, will I be able to produce Vm voltage across my load? No, right? Because after the total it will only reduce and here it will be naturally commutated, SCR will turn off. So I won't be able to get my peak voltage Vm. So here what will happen? This will be Vm sin alpha, because this will be the peak. If let's say I trigger my SCR at this region, this will be the only peak that I get. After that the SCR voltage is always reducing. So after pi by 2, this is the pi by 2, right, where I get the peak value. After this the SCR voltage will always reduce. So the instant at which I will trigger, that will be the maximum value that I can generate across my output. After that it will only reduce. So this will be Vm sin alpha by R. Okay. So alpha, if alpha is greater than pi by 2, obviously it has to be within this range. So I'll write down the range. It has to be between 0 to pi by 2, or if my alpha is between pi by 2 to pi, right, then this will be the peak. This will be the peak. I have explained you why this will be the peak. Now let's go to the case 3. Case 3 is from pi to 2 pi. So what is happening? Natural commutation, right? At omega t equals to pi, natural commutation happens. Okay, at omega t equals to pi, natural commutation happens. Hence this will be 0 amperes of current. This will be 0 amperes of current. Hence what can I say? Is that SCR will be in reverse blocking mode. Why? Because the voltage across it. Why this will be 0 amperes current? Because SCR will be in reverse blocking mode. I have already explained it in the first case, right, where I was analyzing the forward blocking mode and reverse blocking mode. So why? Because my Vt will be less than 0, or I can say my VO will be less than 0. And if VO is less than 0, what will happen? Like the current will try to flow in this direction, which is never possible. Current can never flow in this direction. That's why it is not possible. IO will try to be 0, but not possible. Not possible. Okay. So basically what will happen is that my IS, it will be same as forward blocking mode. IS equals to IT equals to IO will be equals to 0 ampere. My VO will be equals to 0 because it is IO into R, which is equals to 0 volts. My VT will be equals to VS. This time my VS is negative, right? VS is negative, hence my VT will also be less than 0. Hence it will be reverse blocking mode. Hence proved. Okay. Whatever I have assumed that is correct only. Whatever I have assumed that is correct only. Now these are the plots. These are the waveforms for our single phase half wave rectifier. So these are the waveforms. So supply is this pure sinusoid, right? And depending on the alpha sine and alpha, my output voltage will change. If I trigger at alpha 1, output voltage will start from here, because after this, right, current is 0, hence VO is 0, already proved in case 1. Now this is the case 2 where angle is triggered and VO is equals to VS, so it will directly mimic the supply. Then again case 3, pi from pi to 2 pi, it will always be 0 because no current is flowing. So the voltage will be something like this. It will always be 0 here, right? It will always be 0 here. So this will be the output voltage. So this is the output voltage waveform. All cases are explained over here. And alpha 1, alpha 2, alpha 3 over what? So alpha 1 is lower than alpha 1 is between 0 to pi by 2. Alpha 2 is exactly at pi by 2 and alpha 3 is between pi by 2 to pi. So if I observe here, my peak voltage across the output is Vm in this case, right? In when alpha 1 is between this. If alpha 2 is exactly pi by 2, peak voltage will be Vm only at one instant. And after this, right, I will never be able to achieve that Vm peak voltage. My voltage will always be lower than what? Vm sine alpha 3 at the point at which the SCR is triggered. Okay. And what is Vt? So Vt, right, it blocks voltages. So Vt will be equals to Vs in case 1. In region 1 in the forward blocking mode. Then as soon as the SCR is triggered at Vm sine alpha, at alpha, the voltage will go 0 because switch has turned on. The voltage across the ideal switch is 0. Then at pi, omega t goes to pi at case 3, then again the SCR turns off, and if the SCR turns off, what will happen? It will be in reverse blocking mode. Hence the angle like this will be negative, right? This will be totally negative. It is in reverse blocking mode. Then again this same cycle repeats. Now there are few results here. What are the results? This is the first result, that is VO average. Now from here, the educators, what they do is they try to memorize the formula. But what I will tell you is just memorize how we are deriving this. Just memorize how we are deriving this. Obviously, if you are good at remembering formula, you remember. That's always an option. But if you are not that good at remembering, what you do, how we are deriving this, you understand that. Then in the examination hall, try to derive this and do a bit of sanity check to understand whether whatever I am deriving is correct or not. I will explain all those things. So what is the VO average? VO average is the average voltage because no negative portion is there. So VO average won't be 0. VS average, if you observe, is 0 because average across the sinusoid over a cycle is 0 always. I'm getting average voltage and that is what I wanted. I wanted the DC component. That's why I'm interested in the average component. Okay, what is VO average? VO average will be integration from 1 by T of VO of T. So if I integrate this from alpha to pi, because from alpha to pi only this output voltage is existing. Other than that, it is always 0. So I'll only integrate from alpha to pi and it will be divided by 2 pi because it is repeating after every 2 pi. Okay, so you will get this one. Okay, how much second does it took to derive? 2-3 seconds. It's good to remember. Even if you can't remember, it will take you to derive 2-3 seconds. If you understand the converter very well, right? It is converting from alpha to pi with a pure R load. Okay, that you have to understand. That much you have to know. Okay, and you don't need to remember this. What will be my IO average? In this case, right, my IO average will be simply because my VO is equals to IO into R. So my IO average will be simply VO average by R. So I will just remember, like even if you want to remember, I will just remember this formula and I can derive my IO average anytime. It will be simply just VO average by R. Then the RMS value, right? RMS value, the formula for RMS I have explained in my network theory. How to compute RMS over a period. So again, it is 1 by T VO whole square dt whole under root, right? So it will be 1 by 2 pi alpha to pi Vm square sine omega t square d omega t half. Okay. Next, like I will do this in the notes. I will put this in the notes, but you try to derive by yourself how you are computing this. So for this, I will recommend you remember, because this will take higher amount of time to derive. But still, if you want to derive, if you are good with trigonometry, if you are good with integration, this also won't take you more than 30 seconds to derive. Okay, you can derive this as well. I will write this. I will write the derivation. How did it come through this formula? But you can integrate, right? This you have to convert it into double angle formula, and from there you will derive this further. Okay, so VORMS will be simply Vm by root 2 pi minus alpha plus sine 2 alpha by 2 whole under root. And if you want to find IORMS, this will be equals to VORMS by R, but this will not always be the case. I will explain when this will not be the case as well. Okay, so if you want to compute for uncontrolled, right, uncontrolled average voltage and control. So if you remember in the periodic quizzes, there I have derived the average voltage expression for half wave rectifier. So if you put alpha equals to 0 here, you will get the expression for half wave rectifier, which is equals to cos 0 is 1, so this will be Vm by pi. Now this is how you do the sanity check, that okay, for half wave rectifier the average voltage was Vm by pi. If I put alpha equals to 0, this will also become a simple uncontrolled half wave rectifier, and with this formula it is coming Vm by pi. So I am correct, whatever I have derived is correct there as well. If you put alpha equals to 0 here, if you remember, in the half wave rectifier it was simply Vm by 2, the RMS output voltage. Okay, here if I put alpha equals to 0, this will be pi, and sine 2 alpha is 0, so pi under root and pi under root is getting cancelled, and I am getting Vm by 2. So again, this is a good way to check whether whatever you have derived is correct or not. Okay, and IORMS is simply VORMS by R. Okay, like I have already explained, right? You put alpha equals to 0 and you can convert from controlled to uncontrolled rectifier. So put alpha equals to 0 and all the expression will be present, and these are just the ripple factor, all those things. So this you can derive, right? You know what is ripple factor, and you know what are ripples. Ripples are what? Basically the AC component. So it will be VORMS minus the DC component VO average. So I've already explained what is VORMS. I've already derived what is VO average. So from there you can derive the ripples. You can derive the ripples for current as well. And what is the ripple factor? It will be simply VO AC upon VO DC, and you can derive from here. Okay, so all these things you can derive, no worries. Now what is the efficiency of converter? If nothing is mentioned, efficiency of converter will always be VODC by PO. So how do you convert? How do you find out VODC? VODC will be simply the DC VO square average divided by R. This is the DC power that is being dissipated in the load. How else can I write it? I can write it as IO square average into R. Okay, this is the DC power. Or how else can I write it? So what is VO average? VO average is IO average. So I will take one VO average as it is, and other VO average I will write I into IO average into R. So if I write IO average into R, RR will get cancelled, only this one will remain. As promised, I derived how do we get for a DC load, what is the PODC. For a DC load, the power dissipated in DC will be VO average into IO average always. Okay, so you can like write down the expression of VO average and IO average, and you will see if you put alpha equal to 0, right, you will get 40.5% that we derive there as well in the half wave rectifier case as well, right? So all these things you can do, or you don't need to remember this. Just remember this, right? Just remember this. Just remember how you derive VORMS. Just remember how you derive VO average, and from there you find the converter. You don't remember this. Don't remember this. Don't need to remember. Just for formula point of view, for the good representation, I have to write all this, but you don't remember this. Now, one thing you have to understand is that if your PO is positive, right, that means your load is dissipating power. Or I can say load is absorbing power, right? Load is absorbing power. Now if your load is absorbing power, that means power flow will be from, we'll write here, will be from source to load always. As PO is 0, it is absorbing, so power can only flow from source to load only. So in short, right, I write this like this. This is just my notation, that this will be like this. Power, just hold on. Power will flow from source to load. Okay, this is the flow direction of power. So in this case, basically in this case, it is a one quadrant converter. Why? Because like we'll draw the quadrants. Like let's say this is VO and this is IO. My VO and IO will always be positive. VO, if whenever my VS becomes negative, VO is equals to 0. So I'm operating in this quadrant only. First quadrant, okay? And whenever my converter is ideal, hence my PO will be equals to PS. There won't be any switching loss when converter is idle, right? So these things you need to keep in mind. So there is one more term known as ripple frequency. What is ripple frequency? Basically, ripple frequency is also referred to as the frequency at which the output voltage operates. Okay, so the input voltage is at frequency Fs, right? Fs. Now what is the frequency of output voltage? It is also Fs, right? Because it is repeating after every 2 pi. Input was also repeating after every 2 pi. Output is also repeating after every 2 pi. So in this case, our ripple frequency Fr will be equals to Fs. Now there is a term known as ripple, like pulse number. Pulse number is basically what is the multiplier that is multiplied with the supply frequency to get the ripple frequency. So like how many pulses am I getting in one cycle of input, right? How many pulses am I getting at the output in one cycle of input? So in one cycle of input, I am getting only a single pulse, right? So that's why in this case n will be 1. In this case n will be 1. So there are few theoretical points about ripple frequency is written that ripple frequency influences the design and size of the filters/converters. Ripple frequency influences the design and size of filters/converters. Higher ripple frequency simplifies filter design. High ripple frequency simplifies filter design because like it specifies how many ripples I have, right? How many ripples I want to reduce my ripples as much as possible. Sometimes it's called the first non-zero frequency signal in the output. Okay, all these are theoretical terms that you need to know. Okay, so sometimes this n, right? This n also is written as P. Okay, this can be written as P as well. Basically the pulse number. N can be written as P as well. This is the pulse number. Okay, so whichever way you define, because n is used for harmonics as well, that's why we define P. So how many pulses are there in one cycle of the input? Number of pulses in the output in one cycle of input. Okay, that is the definition. And pulse number, there the definition is given. You can like read all this. Like we use filters and all this to reduce the pulse number. Okay, with an increased pulse number, peak to peak voltage fluctuations decrease, making the output more like DC. So if the pulse number increases, right, what will happen is, like when you will study about 3-phase rectifiers, they will see the average output voltage will be much higher. Much higher than this case. When you will derive the formulas, there you will understand. Practically, we use 12 pulse converter, commonly used in high voltage DC applications. That is, in our transmission lines, we use 12 pulse converter. Okay, all those things we will study later on. Okay, so let's analyze the supply now. We have analyzed the load side. We haven't analyzed the converter yet. We'll analyze the converter as well, and now we'll analyze the supply. Like we have analyzed the converter as well. Now we'll analyze the supply side, right? We'll analyze the supply side. So for voltage is pure sinusoid, right? So its RMS will be simply Vm by root 2. Its average will be 0. What is IS average? As everything is in series, so IS average will be equal to IO average. That is this formula. Okay, you don't need to remember this. Just remember VO average, and from VO average, you will be able to derive everything. IO average, IS average, everything. What is IS RMS? IS RMS will be simply again IO average, because IS is equals to IO always, and this will be this formula. Okay, so you don't need to remember. You can always derive. Now, another important like analysis about supply is power factor. What is the power factor? Again, if you observe here, what will happen is everything won't get converted. Okay, and there will be harmonics in the AC side of the supply. As DC current is flowing through the like what is a generator? Generator is generally alternator. We use generator, or you can say, or supply. This you will understand in machines that our supply voltage is given out from the alternator, right? For now, you just understand that in the supply, some DC current is flowing. That is very bad. Heating will happen. I already explained why. Okay, and the starting, and there can be insulation damage and all those things. Okay, so all those things degrade the power factor of the supply, and we want our power factor to be as much near to unity as possible, right? So we use power factor correction techniques that we will understand in machines and power systems. Okay, not here. So our power factor will be equals to cos phi s PS by SS. This I've already derived. Now, in this case, what is the power factor? In this case, what is the power factor? For ideal, I've already explained, for ideal converter, for ideal converter, my PS is equals to PO, right? Hence, PS equals to PO, what I can say is simply, I've already written it out, VORMS whole square by R, right? Or I can write it as IORMS whole square into R, or I can write it as this, right? VSRMS into ISRMS into cos phi. Why? Because this is PO is equals to PS, right? PO is equals to VS. So I can write it like this. I should have written it like this, that PS is this, right? PS is equals to this and PO are equal to this. Okay. So what will be my cos phi is? This is cos phi is, right? What will be my cos phi is? Cos phi is will be PS upon SS, or I can write it will be IORMS whole square into R divided by VSRMS into ISRMS. Okay. VSRMS into ISRMS. So now can I simplify it? Yes, right? I can simplify because IORMS and ISRMS are same. So how much further can I simplify? You can simplify it like this. So this will be equal to simply IORMS into R divided by VSRMS. So what is this? This is simply VORMS, right? IORMS into R is simply VORMS. So what I can write, my cos phi is will be VORMS divided by VSRMS. Now what I can do, I can find out the maximum possible power factor. What is the maximum possible power factor? So what is the VORMS formula? VORMS formula is Vm upon this, right? VORMS is Vm upon, except the R, it is this, right? It is this. Okay. So I can write like this. It is, I will just copy this. I'll just remove the R. R won't be present, right? This is just the VORMS. And what is VSRMS? It is always Vm upon root 2, right? It doesn't care about any other thing. So this will become Vm will cancel, and this root 2, this will become root 2, this will become under root 2 pi into this, right? Now what is the maximum power factor that I can possibly get? I will get the maximum possible power factor at alpha equal to 0. Okay. So at alpha equal to 0, my cos phi is will be 0.707, and I have already told you, like if you just compute the angles of the current, right, it will be somewhat lagging than the voltage. So obviously it will be lag. It will be lagging. Okay, it will be lagging. You can find out from the Fourier series, analysis. Fourier series. Okay. So this is the maximum for a half-wave rectifier that I can get, maximum power factor for a half-wave rectifier. So this is a good result to know. Okay, even if you don't remember, you can always derive it, but it is a good result that you should know. I will only be able to get a worse power factor than this. This will be the best possible power factor that I can achieve in a half-wave rectifier with pure resistive load. Okay, pure resistive load. Now here few parameters are there for the converter. We have analyzed the supply, we have analyzed the load. Now we will analyze the converter. What is the conduction period of this here? This I have derived previously as well. This is the simply omega into T on is equals to pi minus alpha. So if I divide by omega, it is the conduction period. What is the natural commutation time? This is defined as Tc. Omega into Tc will be pi, because from pi to 2 pi it is in the reverse blocking mode. What is the peak inverse voltage? This is also a very important criteria. Peak inverse voltage is the maximum reverse voltage that may appear across a device. This I have explained in my prerequisites as well. So in this case, right, PIV is Vm, because when the ACR voltage is at omega t equals to 3 pi by 2 here, 3 pi by 2, it is expressed in the peak voltage, that is minus Vm. Okay. So yeah, this is the case. Now where did I go? Here, right. So there is a term known as rectifier factor, because engineers, we have to take care of the practical world. Because if I just, let's say my this voltage is 230 volts RMS, and 230 into root 2 will be peak. Now I get a ACR rated 230 into root 2 peak, right? And I connect it. What can happen? The voltage can fluctuate, right? You have seen like your lights get blasted or lights get turned off or lights get damaged due to the voltage fluctuations. So if the voltage fluctuates, the device can get damaged. So obviously I have to have a safety factor which I can take in consideration while buying the SCR. If the peak voltage that is happening across the supply is 230 root 2, I will take a safety factor of 2. So I will double the rating of my SCR so that even if the voltage increases drastically, then also my SCR won't be damaged, then also my light won't get damaged. Okay, it won't allow that current, right? So that's why we take a safety factor. That is the basically the engineer's intuition. It is the voltage rating by the peak inverse voltage, peak inverse voltage that will appear across the diode. So voltage rating, let's say I am taking a rating of 2 Vm, right? Voltage rating SCR of 2 Vm, and PIV will be Vm. So 2 Vm upon Vm will be 2. So safety factor will be 2, because even if the, let's say the peak voltage is 100 volts, even if a peak voltage of 200 volt appears across the SCR, I will be safe. That's why there is a term known as safety factor. Now, what are the few points that you need to note while solving questions of rectifiers? Observe whether the supply is given. The supply given is in terms of RMS or maximum. So you might say, sir, what are you saying? RMS or maximum? I will be able to easily identify. Trust me. Many students make mistake on this, and if you make mistake and after the examination you come back and you realize that instead of RMS I had to take a maximum, you will be destroyed yourself. So carefully look at the supply whether it is defined as peak or RMS, because if you make a mistake in that, you will remember all the formulas, everything you will do correctly, but because you assumed it as maximum and it was supposed to be RMS, you got the answer wrong. So just try to analyze the supply, look at the supply carefully. Identify the type of load. What type of load is? For now we have just studied R load, so everything is simpler, right? But once you study more things, it will be R, RL, RLE, things will become a bit complex. So you have to identify what type of load there is, and also you have to identify what is the triggering angle of my SCR, what is the periods of conduction and commutation and forward blocking mode, reverse blocking mode, all these things you have to identify. So basically this was it for the first lecture. Like, this was a long lecture, but I have tried to give you a brief overview of rectifiers, what do we mean by rectification, and I have also taught you the whole half-wave rectifier with pure resistor load. In the next lecture we'll do questions on half-wave rectifier with R load, and from there the more concepts will be clarified, right? Whatever we learned here, we'll apply those and more concepts will be clarified. Now this is how you analyze this here, but while solving the questions, that will be of different approach. So your approach should change with the question that is being asked. So how do you write the short notes for this? Just write, like for ripple, right? You write it VOAC by VODC. Then you, in your mind, you think, okay, what was VOAC? VOAC was VORMS whole square minus VOAC whole square was equals to VORMS whole square minus VODC whole square. And you can find the ripple factor, you can find the ripples. Okay, what is the TSD? TSD is the IH RMS by IS1 RMS, basically the fundamental upon IS RMS. What is IH? IH is again basically IO RMS minus IS1 whole square. That is my harmonic, and IS1 RMS is already present. So like that you remember. Don't just write down the results. Don't just write down this result, right? This result, like this IO RMS result. You just need to divide by R, right? That only you write. Okay, that only you write. Just you divide by R. Try to remember only this, and through this you derive other things. So that's how I used to remember. Okay, so that's it for this lecture, and I will see you in the next lecture. Thank you for watching.